Okay, now the electric field for an electromagnetic wave points in a particular direction. And so as the wave moves through space, this direction of the electric field traces out what we call the plane of polarization. In this particular case, the electric field is oscillating along the y-axis, and therefore it is a vertically polarized wave, and the magnetic field oscillates in the horizontal plane. We could imagine that we start out the electric field oscillating along the z-axis like this, in which case we would have the electric field in the horizontal plane, and as it moves down the x-axis, it would trace out a horizontal plane of polarization. So this wave on the top is a vertically polarized wave, and here you see the same wave as it comes out at us. It's moving toward us. The electric field is oscillating up and down, and the magnetic field is oscillating perpendicular to that, horizontally left and right. And it's important to note that both E and B are always perpendicular to the direction of motion. Therefore, it's a transverse wave. We could imagine oscillating the electric charge in the horizontal direction that produces an electric field, for example, in the horizontal direction, and this would give rise to a horizontal plane polarization. We could also orient a wave at any angle with respect to the vertical or horizontal to produce a wave which is basically a combination of both vertical and horizontal. In this particular case, we see the electric field oscillating at 30 degrees relative to the y-axis. So polarization is a concept that tells us which direction the electric field is oriented and what the plane of that electric field as it moves is traced out. The way in which we can assess polarization or produce it is by choosing a particular kind of polarizing filter. In this particular case, this polarizing filter is a thin sheet of plastic made of polymers. You can imagine these as long molecules extended along the vertical. And those long molecules have lots of electrons in them that can respond to the vertical portion of this electromagnetic field, or this wave. This diagram right here denotes an unpolarized wave. It shows E pointing in all different directions. Notice they point always perpendicular to the velocity vector. But nonetheless, this is called unpolarized light because it doesn't have a particular direction in which the electric field points. As that wave encounters this polarizer, the polymers in the vertical direction can respond to the electric field in the vertical direction by allowing charges to move up and down along those molecular chains. Because they are vertically oriented, the electrons have the freedom to move up and down, and therefore they will respond to this electric field and absorb it. And so the vertical component of the electric field, when it goes through this polarizer, is absorbed and removed from the light. On the other hand, the horizontal component causes electrons to want to move left and right, but they can't because there's no path that allows them to move in that direction. And as a result, that portion of the wave is not absorbed and in fact is passed. So this kind of polarizer, a sheet of plain polarizer made of polymer, can produce polarized light out of an unpolarized beam. Here we have the unpolarized beam. What survives the sheet and does not get absorbed is that portion of the electromagnetic field that is horizontal. So this is what we can do to produce polarization. We can also use it to measure polarization. If a polarized wave is coming at us, we can rotate the filter and figure out which way the polarized wave transmits and which way it absorbs. And when we find out which way it transmits and absorbs, we can infer what its state of polarization is.